Okay, so we're going to look at the fundamental theorem of calculus. We talked about this in class the other day, and it's got this really interesting looking formula. But basically, what'll help you is if you can what'll help you with this. So if you can keep in mind that if you're taking the derivative of an integral, and let's just keep it something simple like the integral of from 0 to 2 of x squared dx. What you're basically doing is undoing the integral with a derivative. Okay, so if we let's take this guy off for a sec. Let's just think about what we've learned so far about integrals and look at maybe a couple of examples just real quick. So if I take the derivative of x squared, I'm going to get 2x. If I integrate from, say, 0 to 2 of 2x dx, then I'm going to end up with x squared, and then I'm going to evaluate x squared from my stop minus my start. So I'm going to look at 2 squared minus 0 squared. Okay, but look at what the derivative in the integral did. They gave us, they undo each other, or they work well with each other. They're not quite inverses of each other, but the derivative creates something that we can take the integral of to get back to the original function, and that's basically what we're saying with the fundamental theorem of calculus. So if you look down here at these two examples, just follow the pattern, and when you follow the pattern, everything else kind of you'll start to understand it kind of the more you work with it. So basically, all I'm going to have down here on the bottom is cosine x, and that's my function. Okay, this is what my f of x would be for this guy using the fundamental theorem of algebra. Over here on this guy, f of x would be 1 over 1 plus x squared. So it really is not a horrible hard thing, but it's just different, and it is based on pattern. So try and follow that pattern through as you're doing some work. So let's look at another example here. What about with the chain rule? Now we talked about this also in class, and when the chain rule shows up, what we want to do is and I didn't show you this because we were exploring, but let's imagine going from 1 to u instead. And so what is u? In this case, u would be x squared. Okay, so what would du dx be? That would be 2x. And so if I'm trying to find the derivative of cosine t dt, and I take the derivative on both sides, so I do my d dx and I do my d dx on both sides, then what's going to happen is I can't forget what, now that I've substituted my u, what I'm really doing. And the dy dx we get, that's going to be on the left, no problem. But on the right-hand side, what are we going to do? We're going to look at the derivative of y with respect to u times the derivative of u with respect to the x. And so that's where things now become a little wacky, because we've got this un up here. So keep in mind, here's my u, here's my derivative of u. So when I work my chain rule out on this guy, what I'm going to actually really have is d du, okay, from 1 to u cosine t dt times my du dx. So this is really the step that I'm processing here. So this guy is going to end up being cosine u. This should be a cosine right here. I'm really going to have cosine u times du dx. Well, what was my u? My u is x squared. What's my du dx? 2x. So I end up with 2x cosine x squared. So it's really, you know, it really is practice of doing a substitution and then chaining out what you get with your derivative inside there. Okay. So some more things that could happen is, say we could have where y equals our integral growing from x to 5. The problem with this is it's upside down. So what you would need to do in this case is just go ahead and rewrite your integral, but follow the rules that we learned the other day. So this is going to go from 5 to x of 3t sine t dt. And then over here on the other side, what we would want to do is kind of split this guy up into a couple of different pieces, potentially, so that we could get it to work out a little bit easier. And the way that we're going to work on this one is we're going to look at it from 0 to x squared. Okay, of 1 over 2 plus e to the t. And again, we're going to use our rules that we have learned, some of our basic rules about integrating minus 0 to 2 x of 1 over 2 plus e dt. And so when you combine these two guys together, remember you're going to have stop minus start, so you're going to end up with x squared minus 2x. And then when you rewrite them in this form, you're still going to have the x squared minus the 2x. So it doesn't really change anything for us. Now, one thing it does do is we've got to pay attention to some chain rules here. So we're going to have a 2x on this guy and a 2 on this guy. But we'll look at that in just one second. So back over here to the left, when you do your derivative, you're taking the derivative of the whole thing. So it's not too bad at all. It's just going to be minus 3x sine x. And that's all there is to that guy. He's really not too bad. Over here, though, you know, once we kind of get figured out what our limits of integration should be, now that we can go through, and don't forget that if we let u equal x squared, then du is equal to 2x dx. Or du dx would be 2x. And then on this side, if we let u equal 2x, then du dx is going to be 2. So when we do our work down here, what we're going to end up with is 1 over 2 plus e to the x times 2x minus 1 over 2 plus e to the x times 2. And so we can simplify these down a little bit more, and we're going to end up with 2x. Oh, gee whiz. This would be an x squared here, and this would be a 2x here. So what we're going to end up with is 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So again, these could be really tricky, hard, nasty problems, but they're doable. Just make sure that you take your derivatives where you're supposed to take and then substitute in where you're supposed to substitute in. Okay, so here's one that's a little bit trickier now. Find a function y equals f of x with the derivative dy dx equals tan x. All right, no problem. By the way, we want f of 3 to equal 5. Okay, no problem. So they're giving me my derivative right here. Okay, and they want us to go back and find a function that this is related to. Well, based off of what we just have learned, we know that y equals, and they're telling us the function for f. They're like right here, this guy right here, that's a 3. So that's what x is. So they're telling us we're going to take an integral from 3 to x, and then we're going backwards now. So instead of saying tan x, we're going to say tan t dt. Now, the way that this function is written right now, what we're saying is this function at 3 would be equal to 0. So in order to make this work out to the plus 5 part here, all you're going to have to do is add 5 at the end. And that's it. There's no like super tricky math going on here. There's no weird things. We're just going in the reverse order. And by the way, here's your x coordinate here, and here's your y coordinate, your plus coordinate, plus y coordinate here. And you'll remember when you graph things, this last guy tells you where you're going to be on the y-axis. So if we're at 3, we're at 5. And these are not hard. Don't let this part be hard, okay? Okay, here's the part 2 part of the fundamental theorem of calculus, which we've seen a few times. We just haven't called it the part 2 yet until in class recently. So the fundamental theorem of calculus part 2, if f is continuous at every point on the closed interval a to b, and if f is any antiderivative of that function on a to b, then you take that function of b minus your function of a. And one of the easier ways to kind of remember all this is to remember that this is going to be where you stop, and this is going to be where you start, which matches this guy and this guy. So that's kind of where you're going to end up. But we've done this before. We've looked at it before, and this is going to give you an area under a curve. And so we're going to learn a lot of rules on how to deal with integrals and things like that. But let's just take a look at one down here real quick. So find the area of the region between the given curve and the x-axis using antiderivatives. And so now we're wanting to go from 0 to 3. So let's just get us a little line in here at 0. He's going to grow really slowly. Hopefully he'll stop where he needs to. And let's take this guy off. And then let's get another guy on there from 0 to 3. So now we're looking out here at 3. So right about here. And what's going to happen is we want to find the area under the curve from the two dotted lines, okay? And in order to do that, we have to take an integral. Okay? And when we take that integral, what we're going to do is add the area between the curve and the x-axis together. And so when we do that, we're actually going to look at these two pieces right here. If I can get my colors to work, it's going with some lag. Holy moly, look at that guy. I'll just draw it. Let's get this guy out of the way right here. We don't need him. There he goes. All right. So going from 0 to 3. And when we do this, we're going to just get the area under the curve. So we're looking at this part of the curve right here, right in this area, and the part of the curve right here in this area. So when we do that, we're going to have a top minus a bottom kind of a thing. So here's our setup then. Following our fundamental theorem, our setup is going to be the integral from 0 to 3 of 4 minus x squared dx. And so we can integrate this. This is going to be 4x minus x cubed over 3. And this is the part that we would call the antiderivative. Okay. And so what we're going to do is we're going to put our stop minus start. So we're going to do 4 times 3 minus 3 cubed over 3. That's the first part, minus, and then where I started at 0. So 4 times 0 minus 0 cubed over 3. Well, the second guy is going to be 0. He completely goes away, so we don't have to worry about him at all. Okay? And this first guy then is going to become 12 minus 9, which is 3. So using the antiderivative, it's not a hard thing for us to solve this guy out. We can do it. It's no problem at all. Now, one thing that we can do is use your calculator to double check you, and you can find that the area, the total area, would come out to be 3. The other thing that we can talk about with this graph is the actual area between the curves as a total, as an absolute value of area, in which case we would need to split our integral up and look at the area under the curve from 0 to 2, and then the area under the curve from 2 to 3. And so if we were going to find the entire area of this region, so this would be total area. Okay? But if we're looking for the area between the region between the two curves, if we're looking for the total, like a positive type, like the amount of area actually between the curve and the x-axis, we would look at the two integrals, but this time we would look at them like this. And then we would add the second part. It would be minus actually the second part. And so on both of these, the antiderivative would be the same thing. So I would do stop minus start here, which is going to be 4 times 2 minus 2 cubed over 3. minus the 0. So that's the first integral. And then minus the second integral now would be the stop, which is going to be 4 times 3 minus 3 cubed over 3. And then the second guy here, whoops, not 0, but what? Now it's a 2. So it's going to be very similar to what that first integral started with. So 4 times 2 minus 2 cubed over 3. And so now I can put these guys together. So this would be 8 minus 8/3. And that would be 24 minus 8, which is going to be 16/3. Minus, and then over here I would have 12 minus the 9, which is 3. Minus, and then 8/3 again. So this would be to get a 3, that would be 9 minus 8. Is that right? 9 minus 8. I feel like I've got something not quite right here. 4 times 3 minus 3 cubed, 27 divided by 3 is 9. 12 minus 9 is 3. So 8 minus 8 cubed, which is 16. This should be 16. 16 cubed. Let's clean that up a little bit. Which in this case then is going to be -7. So what I have is 16 cubed minus -7 cubed. And that'll give us 23/3. I think I said cubed, but 23/3. So this right here is the actual total area under the curve from 0 to 3 of 4 minus x squared. And if we add them up as a positive area here, and then as a positive area here, and then a negative area here, then that sum would be 3. Okay. So again, these are trickier ways. They're a little interesting, but you know, if you read through your directions and pay attention to exactly what you're looking for, these are the different ways that you would work your integrals. And lastly, you can use your calculator to double check you on everything. I've shown you some tips and tricks in class. You can also check my YouTube channel for to get those directions again if you forget. But remember that if you are looking for the total area between the curve and the x-axis, then you want to look at the absolute value, because you do want the total area. If you're just interested in the area that you would get looking at both the positive for being above the x-axis and the negative for being below the x-axis, then you would go ahead and look at an integral without the absolute value signs, and that would just give you an area either positive or negative. So make sure and read the question a little bit carefully. And here I've shown you the difference between a possible negative area answer and a positive one. This guy on the left is your regular trig curve, and when you add up all these areas underneath, they may make a difference and give you a negative value. However, when you add up all the areas here, everything's going to be above the x-axis. So this is going to give you a grand total of positive area. So just kind of pay attention to what you're working on. And as always, if you have a question, you can ask me, and we'll get you all fixed up.